Hi, so we are team 4 and we completed this project named membrane capacitive deionization to fulfill the requirements of our course named electrochemical engineering. I am Mahmudul Hassan. So here we can see the outline of our presentation today. We'll show the objectives, introduction, and how we did these experiments, and later we'll show how we analyzed our data. That includes energy, normalized adsorbed salt, and electrochemical impedance spectroscopy. At last, we'll show you the findings from our project. So the main objective of this project is to become familiar with MCDI technology. We also wanted to determine energy use per adsorbed ion, and we wanted to measure how the energy consumption scenario looks like for NaCl and KCl. We also determine the resistances of the MCDI cell that contains membrane and spacer channel ohmic resistance. Also, it contains diffusion of electrolyte into electrode ports, the resistance that occurs for that case. So we then compared those resistances for NaCl and KCl, that means different solutes, and we verified our results with related literature. So membrane capacitive deionization is a technique where electric field is used to pull ions from water and onto electrodes. It is normally used to treat brackish water streams. That means the water that contains has 5,000 less than 5,000 ppm of salt. This is a very important technique because fresh water is a limited resource, and salt in water utilities can cause scaling and corrosion of equipment. Also, it is a very energy efficient technology because while discharging we can recover electrons, which is one form of electricity. So here we can see the two cycles of MCDI operation. During charging cycle, constant current is applied to the cell, as a result of which ions move through the ion exchange membranes and adsorb to electrodes. That means we are providing some form of energy for the ions to get adsorbed to the electrode. During the discharging cycle, the polarity of the cell is flipped, and as a result of which ions are dissolved and electrodes are regenerated. So we are getting some energy back from the discharging cycle. So here we are using ion exchange membranes because it ensures that due to donor exclusion, we can selectively pass ions. We know that like charges repel each other. So if the membrane contains a particular ion, the counter ions will not be passed and the co-ions will be passed through that membranes. As anion exchange membranes, we are using PUB-TPX membrane, which is commercially bought from Orion, and it allows negative charge to pass, and it allows cations to pass because it contains negative charge. And we are, as cation exchange membrane, we are using sulfonated polysulfone, which is synthesized in the lab of Professor Arges, and, uh, and here the membrane contains positive charge, so it allows anions to pass. So one question that came into our mind during this doing this experiment is that why constant current operation is selected, because we can do this experiment in two modes: constant current and constant voltage. Constant current mode is more energy efficient compared to constant voltage operation, and also from the graph we can see that we can actually we'll get a more constant effluent concentration from the constant current mode operation rather than from constant voltage operation. Also, if we operate our MCDI system at a constant voltage mode, then excessive current can flow through the system, and as a result it will cause overheating of the system. So the voltage limit is also set to 1.6 volt because we wanted to avoid water splitting and other parasitic side reactions, and we wanted to ensure large enough current density for salt removal. So my next partners will show you the MCDI methodology and results.